Pluto is a far-off and baffling bantam planet that was once an individual from our nearby planet group's planetary family. However, ongoing surprising declarations by leading astrophysicist Neil deGrasse Tyson and MIT's Michio Kaku have carried Pluto back into the spotlight with a stunning disclosure. They suggest that this frigid world is on a potential impact course with Neptune. But how could this work out, and what might be the outcomes of such a gigantic event? Are we seeing an uncommon galactic peculiarity, or is there something else to this looming, enormous crash? Join us as we investigate the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a bantam planet partly because of its exceptional orbit, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential catastrophic crash between these two planets, which could pose a huge threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our solar system. It requires a stunning 248 years to complete a single orbit. This means that, since its discovery in 1930, it hasn't even completed one full revolution. The intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets, adding layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to understand its strange path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. Yet, the safety of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's similar to predicting where they will go based on their starting positions and how they pull on one another. In Pluto's case, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity work together in a complex manner. The terms alpha libration and scope libration, along with the Vsky oscillation, are key to this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. With respect to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial division is crucial in preventing their orbits from intersecting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned mostly above their orbital plane, providing an additional layer of protection from potential collisions. Another key aspect of this situation is the Vsky oscillation, named after three researchers, Bond, Zippel, and Kai, who studied how objects move in space. It's about how three massive objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational tugging affects how they move, and in Pluto's case, the Vsky helps us understand why its orbit around the Sun is so irregular. Despite Pluto's seemingly chaotic orbit, this oscillation helps keep it moving smoothly over long periods, preventing it from colliding with Neptune or straying off course. The three-body problem helps us understand how these orbits evolve due to the gravitational interactions among these celestial bodies. Studying this helps us learn more about Pluto, our solar system, and distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite these steady properties, Pluto's orbit is actually chaotic. Minor deviations in starting conditions can lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been shown to maintain stability over vast timescales, effectively keeping the chaos in check. Recent computer simulations have also helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps stabilize Pluto's orbit. But Neptune isn't the only planet contributing. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and steady, with a bit of help from Saturn. These simulations show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a steady path for a long time, even billions of years. In essence, Neptune, Jupiter, and Saturn are working together to keep Pluto safely in orbit without running into trouble. These phenomena are essential for maintaining the control and consistency of celestial motions. Without these forces, the solar system would be a much more turbulent and unpredictable place. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a chain reaction that could affect other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is critically important. This knowledge offers a clearer picture of the solar system's dynamic nature. Pluto's position shows how even seemingly unstable orbits can achieve a state of balance through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the erratic nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital disorder, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is distinctly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can drastically alter its long-term path in the vast expanse of our solar system. Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior. One of the most fascinating features of Pluto is its surface, described by a complex tapestry of ice, rock, and other formations. NASA's New Horizons mission, which flew by Pluto in July 2015, provided remarkable data about this distant world. The surface of Pluto includes vast fields, towering mountains, and deep valleys. One of the most notable features is the Sputnik Planitia, a massive heart-shaped plain primarily made of nitrogen ice. This region showcases a variety of landforms, including large glaciers and what appear to be flowing ice sheets. The presence of these features suggests that Pluto may still be geologically active, despite its great distance from the Sun and its low temperatures. Another intriguing aspect of Pluto is its atmosphere, composed mostly of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin but exhibits fascinating seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, adds further complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship contributes to the gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing scientists with a glimpse into its formation. Pluto's orbital characteristics could offer insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a crucial role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is its potential impact on our understanding of the solar system's evolution. The gravitational interactions with nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to shifts in orbits, potentially resulting in collisions or ejections from the solar system. As researchers continue to study the details of these interactions, they may uncover broader insights into the formation and ongoing evolution of the solar system. As researchers continue to study the details of these interactions, they may uncover broader insights into the formation and ongoing evolution of the solar system. Understanding these gravitational forces is not just about observing celestial bodies in isolation, but recognizing the intricate relationships between them, which shape the entire structure of our solar system. This knowledge could also provide valuable context for exploring distant star systems and their planetary dynamics. For example, scientists are increasingly examining exoplanets in other star systems to understand how their orbits may be influenced by nearby planets and stellar objects. The study of Pluto's orbit and its complex interactions with Neptune and other giant planets serves as a model for understanding how smaller bodies behave in the presence of massive gravitational influences. As we learn more about Pluto's orbit and its stability, we gain critical insights into the broader mechanics of planetary systems, helping to explain the diverse range of planetary architectures observed in the universe. Additionally, Pluto's unique orbital characteristics and its relationship with Neptune may also have implications for the study of other objects in the Kuiper Belt and beyond. The Kuiper Belt, which stretches from about 30 to 50 Australian dollars from the Sun, is home to a variety of icy objects, including other dwarf planets, comets, and potential impactors. Understanding the long-term behavior of these bodies, especially those that might interact with Neptune or other giant planets, could help predict the future evolution of the solar system and identify potential threats or opportunities for exploration. As we look to the future of space exploration, missions like NASA's New Horizons will continue to provide invaluable data about Pluto and other distant bodies. The New Horizons spacecraft, which completed its historic flyby of Pluto in 2015, remains in the Kuiper Belt, offering scientists the chance to study even more distant objects in this region. The data gathered from these missions will further refine our understanding of how objects in the outer solar system interact with each other and what that means for the formation and evolution of planetary systems across the galaxy. In conclusion, the study of Pluto's orbit and its potential collision with Neptune, while still speculative, underscores the importance of understanding the complex dynamics that govern our solar system. Pluto may no longer be classified as a planet, but its unique characteristics and position in the solar system continue to offer fascinating insights into the forces that shape celestial bodies. By continuing to observe and analyze the motion of objects like Pluto, we not only learn more about this distant world, but also gain a deeper understanding of the fundamental mechanics that govern the cosmos.